All right, Organic Chemistry 1, continuing on with polar covalent bond. So we just spent some time talking about what a covalent bond is. A covalent bond is a bond where two electrons are shared between two atoms. And a polar covalent bond results when we have a difference in electronegativity between two atoms that are sharing a pair of electrons. Now, what is electronegativity? It's something that you would have covered in General Chemistry 1, and electronegativity is a measure of how strongly an atom attracts electrons in a bond. If you think about electron affinity, that you would have also learned in General Chemistry 1, electron affinity, that deals with this with an individual atom's ability to pull electrons towards itself. However, electronegativity specifically refers to atoms in a covalent bond and how strongly one atom will pull electrons towards itself and how strongly the other atom will pull electrons towards itself. And so we have the electronegativity scale here. This is table 1.1, comes straight out of your textbook, and you can see that the trend of electronegativity is that it increases going from left to right across a period, and it increases going up a group. And fluorine is the most electronegative of all of the elements. Now, ones that are going to be commonly used in this class, the ones that are going to come up over and over and over, are going to be things like carbon, obviously, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine. So I would recommend that you memorize the electronegativities of all the elements that I have highlighted in yellow. And if you're thinking, oh no, it's going to be difficult, well, it's not that bad, because if you just remember that fluorine is 4.0, as you go backwards across the second period, it keeps decreasing by half. So you go from 4 to 3.5 to 3.0 to 2.5 to 2.0 to 1.5, and then you get all the way down to lithium, which has an electronegativity of 1. Also, you need to remember that hydrogen is 2.1. The halogens, you go from 4 to 3 to 2.8, so there's not as big a difference between chlorine and bromine. However, there's another rule that you can use over in the P block, and that's the 1 down and 2 over rule. So if you look at bromine, you have 1 down and you go over 2. So boron, did I say bromine when I meant boron? Boron and phosphorus are approximately the same. You see the same thing for carbon and sulfur. They're both identical. Nitrogen and chlorine, right down 1 over 2, and we have the same value of electronegativity. So again, just some quick rules about how to help you memorize the electronegativity of some of the elements that are going to come up over and over and over in this class. And again, I recommend that you, and when I say recommend, I mean I want you to memorize the ones that I have highlighted in yellow. Well, what is that polar covalent bond? Well, there's 3 types of electron sharing when it comes to bonds. We can have a purely covalent bond. That's a bond that results when the difference between or the difference in electronegativity, I should say, between the two atoms is less than 0.5. So I say difference, delta, in electronegativity is less than 0.5. When you have a difference that's less than 0.5, we have a purely covalent bond. So if you think about 2 carbon atoms, well, the delta En here would be 2.5 minus 2.5, which equals 0. So obviously there's no difference in electronegativity here. Between carbon and hydrogen, my delta En would be 2.5 minus 2.1. You can either put the largest value first, or you can take an absolute value. If you did 2.1 minus 2.5, and you would get 0.4. But 0.4 is a small difference in electronegativity. It's less than 0.5. So that means that whenever we see a compound that possesses only carbon-carbon and carbon-hydrogen bonds, it's going to be a nonpolar compound, right? Because it's a nonpolar, or just a strictly polar covalent bond, which again, we sometimes call a nonpolar covalent bond. So I'm going to move this over here, and I'm going to write here nonpolar. Okay, so if you think back to those molecules that we looked at this morning, butane and isobutane, those are both nonpolar molecules because they only possess carbon-carbon and carbon-hydrogen bonds. A polar covalent bond, that is one where the difference in electronegativity is going to be between 0.5, so greater than 0.5, and maybe I'll put it like this. Delta En will be either greater than 0.5 or less than 1.7. So say, for example, you have a carbon-oxygen bond. Well, what would be my delta En here? Oxygen has an electronegativity of 3.5. Carbon's is 2.5. That gives us 1.0, right? 1.0 is in between 0.5 and 1.7. So this is a polar covalent bond. What does that mean? It means that they're sharing the electrons. However, it's an unequal sharing of electrons. The way that I describe this to students is I say, you know, I have a 6-year-old daughter. Her and I used to like to go to Costco and get a slice of pizza together sometimes, you know, if my wife was shopping. Now, we would share the slice of pizza. However, was it equal sharing? No, there was an unequal sharing of pizza. So we were still sharing it. Right? We both had ownership over the pizza, I guess, but it was an unequal sharing. So the same thing is happening here, right? The oxygen has more of the electron density in this covalent bond than the carbon does, right? Sometimes we draw an arrow to show the induction, right? Showing that most of the electron density is on the oxygen. Other times we draw these delta symbols. The delta, the little d, so this is a lowercase d in the Greek alphabet, this means partially, okay? So it means that the oxygen is partially negative. The carbon is partially positive. This is not an anion. This is not a cation. It's just saying there's an unequal distribution of electron density, and most of it is on the oxygen. Then we can go to ionic bonds. So this is where you have a difference in electronegativity. Delta En, which is greater than 1.7. So say you have sodium and oxygen. I'm not going to show you the calculation, but sodium has an electronegativity of 0.9. Oxygen is 3.5. So you can do the math. That's what, difference of 2.6. And so that's an ionic bond, right? That's a bond where the oxygen takes the electron and the sodium gives up its electron, right? That's where the oxygen gets its extra electron from, so that it has a formal charge of -1. The sodium is left over with a formal charge of +1. And so the cation and the anion are attracted to each other. So you need to know the difference between a covalent, a polar covalent, and an ionic bond. Now, one more thing before we can move on. These are not carved in stone. So these are not, I'll just leave it out. We could say they're not hard and fast rules. What do you mean by that, Mr. Dion? What I mean is that if you were able to shrink yourself down to the size of an atom, you don't see the letter C and you don't see the letter O anyway. Okay, these are just numbers that were developed by human beings. The scale of electronegativity that we use in this class, this is the Pauling scale. It was invented by Linus Pauling. And there are many other scales of electronegativity. Okay, if you take other chemistry classes, you might even see some of those other scales. However, this was, again, just developed by humans. And so you have to kind of take these with a grain of salt. So much so that later on in this class, we'll look at, bonds that are considered polar covalent. Like, let's say we have a bond between lithium and carbon. Now, if you do the math, that would have a difference in electronegativity of what? It would be around 1.5. So you'd say that it's polar covalent, right? The delta En would be around 1.5. So you'd say, well, that's polar covalent, but in fact, we're mostly going to treat it like it's ionic. Okay, so again, these are just guidelines to help us rationalize bonding and also to rationalize reactivity, which is where we're going with all this kind of stuff. Okay, so again, the arrow, right, that's just used to show a dipole. So wherever the arrow points, that's pointing towards the more electronegative element. And the greater the difference in electronegativity, the more polar the bond. Here's that example that I was talking about. The carbon lithium, again, if you do the math, the difference is 1.5 units of electronegativity. But whenever we draw a carbon lithium bond in organic chemistry, we're always going to draw it as if it's ionic. Another example would be, a carbon magnesium is kind of right on the cusp, and we'll always draw that as being ionic. And so you got to take these values with a grain of salt. Okay. Now, if you're wondering, oh, Mr. Dion, are you going to be splitting hairs on the first quiz? Is every question going to be about 1.7, 0001, and what's the judgment? No, of course not. My job is not to try to trick you. It's just to test you to make sure that you understand the content. Well, let's move on And let's take a look at a question. It says, for each of the following compounds, identify any polar covalent bonds by drawing delta plus and delta minus symbols in the appropriate locations. The reason why these are so important is, again, because it's going to help you understand reactivity of molecules later on. Well, let me help you out, because I don't expect you to have had time to memorize all these electronegativity values, but fluorine is 4.0, chlorine is 3.0, carbon is 2.5, and hydrogen is 2.1. So if I look at this molecule here, so this would be chlorofluoromethane. Are there any polar bonds in this molecule? Could anybody identify any polar bonds in this molecule? And again, I hate trick questions, so it's just a real genuine question. Could anybody identify a polar bond? Or are there any polar bonds in this molecule? Yeah, thanks, Warren. Absolutely, right? The carbon-fluorine bond is definitely a polar bond, right? Fluorine has an electronegativity of 4, carbon is 2.5, so the difference would be 1.5. So yeah, there is a dipole, right, going between the carbon and the fluorine. However, in the question, it asked us to draw delta pluses and delta minuses. So let's draw a delta minus by the fluorine because it's more electronegative. And let's draw a delta plus by the carbon, like that. Is there another polar bond? Well, remember that we said polar bonds is having electronegativity between 0.5 and 1.7. So if you look at the difference in electronegativity here between carbon and chlorine, the delta En is right on the nose. It's 0.5. So the carbon-chlorine bond is also a polar bond, right? We have a delta minus by our chlorine, like that. And also our delta plus stays on our carbon, right? Again, if you want to draw dipole arrows, you can draw those. So if I redraw the molecule like this, right? If it helps you to draw a dipole arrow because you would have learned those in general chemistry, by all means, go ahead and draw them, right? You have a dipole going this way, and you have another dipole going that way. Give me a thumbs up in the chat if you follow me on this, the whole concept of a polar covalent bond. So there are exceptions with polar bonds. However, you don't have to worry about exceptions in chapter 1. When we get into an exception, when we encounter one, I will cover it in detail with you. All right, let's take a look at this molecule here. This is acetone. Acetone, which is nail polish remover. You can buy some in the paint section at Home Depot. It's used as a paint remover, so not just nail polish remover. I'll go a little quicker here. There's only one polar bond in this molecule, right? Because remember, a carbon-hydrogen bond is nonpolar, right? And a carbon-carbon bond is also nonpolar. However, there is a difference in electronegativity between carbon and oxygen, isn't there? Right? The delta En between oxygen, which is 3.5, and carbon, which is 2.5, is 1.0. So this is a polar bond, a double bond, and I'm going to have a delta minus by the more electronegative element, and I'll have a delta plus by the less electronegative element. So there is a polar bond in acetone, and it is the carbon-oxygen double bond. Okay, so everybody has to be able to, draw a Lewis structure, identify polar bonds, be able to draw delta pluses and delta minuses in the correct places. All right, let's move on and talk about atomic orbitals. So in general chemistry, you would have talked about the duality or the dual nature of an electron, that an electron was first regarded as only a particle, but then Einstein proved with the photoelectric effect that electrons have wave-like properties, or also that they have particle-like properties. Anyhow, he proved the duality or the dual nature of the electron. And then quantum mechanics came along later on to help us explain the wave properties of electrons. And the solution to the wave equations for electrons gives us a visual representation of what we call atomic orbitals. Now, to distill this into the simplest possible bits of what you have to know for organic chemistry 1 is that you've got to know the different types of orbitals. Now, the only ones that are going to show up in organic chemistry are s and p orbitals. We're never going to look at d orbitals. Now, if we do, it would be pretty rare, but you have to know the shape of an s orbital, right? That an s orbital is a sphere. You also have to know that p orbitals, so these are all p orbitals, are shaped like a propeller or a peanut, or sometimes people describe them as a dumbbell. And there's 3 possible orientations for a p orbital. We see we have the py orbital here, we have a px orbital here, and we have a pz orbital here. So you have to know the shapes of the atomic orbitals. Why is the shape of an atomic orbital so important? Because you have to understand the shapes of atomic orbitals in order to understand valence bonding theory, which we're going to look at in a few minutes, because sigma bonds are the result of the head-to-head overlap of p orbitals, or the overlap of s orbitals, or the overlap of s and p orbitals, right? Pi bonds are the overlap of, or the side-to-side overlap of p orbitals, and we'll talk about that more later on. But you've got to understand that an s orbital, since it's a sphere, has only 1 possible orientation, whereas a p orbital has 3 possible orientations, right? The y, the x, and the z axes. Well, a type of orbital is identified by its shape. Now, of course, there are d and f orbitals, but we won't look at those in organic chemistry 1. What is the significance of an atomic orbital, the s orbital or the p orbital? It's a region of space where there's a 90% probability of finding an electron. So most of the time, we're going to find the electron in that space, whether it's the s orbital or the p orbital. What else do we need to know? We need to know that orbitals that have the same energy level are called degenerate orbitals. So let's say we're talking about 2p orbitals, for example. Right? You have the 2p orbitals, you have the 2px, the 2py, and the 2pz. These are all the same energy level, the 2px, the 2py, and the 2pz. And so these are degenerate, right? Same energy level are degenerate. What else? You've got to know how to construct electron configurations. You've got to understand the Aufbau principle, or the building up principle. That's the principle that states that we start with the lowest energy atomic orbitals, we fill those, and then we move on to higher energy atomic orbitals. You've got to understand the Pauli exclusion principle, which states that each orbital can hold a maximum of 2 electrons, which have spins in opposite directions. And you also have to know Hund's rule, which I call the bus rule, which states that we have the maximum number of unpaired electrons in our orbitals. Now, if you're wondering, what is an Aufbau, a Pauli, and a Hund? These are things that would have been covered in detail, in dirty detail, in General Chemistry 1. And so you have to be familiar with those. So valence bond theory states that a bond occurs when atomic orbitals overlap. Like, let's say we have s orbitals and p orbitals, they overlap together to form new bonds. And overlapping orbitals are just like overlapping waves. If we have constructive interference, it's going to result in a bond, whereas if we have destructive interference, it will not result in a bond, it results in a node. You've got to know how to define a bond according to valence bond theory. So let's take a look at a sigma bond, for example. If we have a hydrogen atom, right? Everybody here should know that a hydrogen atom has an electron configuration, which is 1s1. If I drew a Lewis dot symbol of hydrogen, it would just look like this, a hydrogen with a single dot. If I drew another hydrogen atom, it looks like this, a hydrogen with a single dot. If I draw a hydrogen molecule, it's 2 hydrogens connected by a single bond, like that. And we discussed why that happens, because you have 1 unpaired electron in 1 hydrogen atom with its spin in 1 direction. We have the other hydrogen atom with its electron spinning in 1 direction. And again, I'd like to draw my arrows with the single heads. You can draw a double-headed arrow. There's no problem with that. But then once they form the sigma bond, you have the 2 electrons in that bond, which is a result of the overlap of these 2 orbitals. This is a 1s1 and this is a 1s1. okay, overlapping to form the sigma bond. And we have the two electrons in here that have opposite spins. So that shows the forming or the formation of a sigma bond or a single bond between two hydrogen atoms to form an H2 molecule, right? The reason why we form that H2 molecule is the result of constructive interference between the two 1s orbitals overlapping. We have 1s1 and the other 1s1, and they come together and they make an H2 molecule like that, right? Hydrogen is 1s1, like that. So if we were to take a cross section, on this portion of the molecule here, which is what they're trying to demonstrate in this picture here, you would see that most of the electron density is actually residing in between the two hydrogen atoms in that single bond, which we call a sigma bond. Okay, so when we draw the H2 here, you hear me call it a single bond because there is only one bond, right? Two bonds would be a double, three bonds is a triple, but this is called a sigma bond. Now, molecular orbital theory, this is something that I used to teach in this class. However, it's not covered by the ACS for Organic Chemistry 1 or Organic Chemistry 2. So I'll just kind of go over this very quickly with you because you would have taken a look at molecular orbital theory in General Chemistry 1 for diatomic molecules like H2 or Li2 or dihelium or N2, O2, F2, right? You would have done that probably towards the end of General Chemistry 1. But all you really need to know is that when you have atomic orbital wave functions, they can overlap in two different ways, right? They can overlap to form antibonding orbitals, and they can overlap to form bonding orbitals. So the number of molecular orbitals that you get is equal to the number of atomic orbitals that were used. So let's say we're just talking about hydrogen, simplest possible molecule. We have a hydrogen that's 1s1. We have the other hydrogen that's 1s1. They can either overlap constructively to form a bonding or overlap destructively to form an antibonding molecular orbital. And again, we have two atomic orbitals here, right? These are two atomic orbitals, and we end up with two molecular orbitals, right? 1, 2. Okay, we'll talk about that in more detail in Organic Chemistry 2 if you decide to take that class. The antibonding orbital, all you really need to know is that it's higher energy because it's got a node in it. There we go. So with that in mind, let's move on to something that's really important for my students in Organic Chemistry 1, and that is the concept of hybridization. So I'm going to talk about hybridization just kind of on a blank document here just for a second. So let me see. Can I find a blank document? Here we go. If we take a look at a carbon atom, right? Everybody here should be able to write out the electron configuration of a carbon atom, which is 1s2, 2s2, 2p2. Right? If I was to ask you to draw, the orbitals, we have a 1s orbital, we have 2 electrons in that, we have a 2s orbital, there's 2 electrons in that, there's 3 types of 2p orbitals, we have 1, 2 electrons here. So according to this electron configuration, we only have what? We have 2 unpaired electrons. Well, hold the phone because I just told you earlier today that carbon is in group 4A, right? If you look in group 4A, you have carbon right there, and I told you that you could draw your carbon with 4 unpaired electrons. The reason why is because we saw that if you have carbon in a compound like CH4, for example, okay, how does CH4 bind together? It's going to have the carbon with 1, 2, 3, 4 bonds to hydrogen like this. Okay, well this and this are not explained by this electron configuration, are they? Because here, look, I'm contradicting myself. Look, I've got 1, 2, 3, 4 unpaired electrons, but then when I draw a perfectly good electron configuration, which you would have learned in General Chemistry 1, I've only got 2 unpaired electrons. What's the problem? There's a big disconnect here, right? A huge disconnect. And this is where the subject of hybridization comes into play. What if we take one of the electrons from the 2s orbital and we excite one of these electrons, okay, and we move it into the 2p orbital? This is when we get hybridization occurring. Now, I'm just going to leave the core electrons out. I'm not worried about those because they're not involved in bonding. But then we would have a 2s orbital. It has one electron in it, 1, 2, 3. Then we'd have 3 p orbitals, and they each have an unpaired electron. Hey, perfect. Now I have 4 unpaired electrons, just like I wanted in my Lewis structure. Everything is good. No, it's not. Now I've got a major problem because I've got a carbon atom that has an s orbital, which is a sphere, with 1 unpaired electron in it. And I've got 1, 2, 3 p orbitals, and each one has an unpaired electron in it. That doesn't explain the bonding in CH4. Because if you remember from General Chemistry 1, that when you have an atom that is surrounded by only 4 bonds, it will form a molecular geometry that is tetrahedral. Give me a thumbs up if you remember the tetrahedron, right? And all the bond angles are 109.5 degrees. Okay, so this is a tetrahedron or tetrahedral molecular geometry. Okay, so everybody should have been introduced to molecular geometries: linear, bent, trigonal, pyramidal, right? Tetrahedral, seesaw, octahedron, square base pyramid, all that good stuff. Square planar, right? All that good stuff. And you should have been introduced to the concept of a tetrahedron. Well, how could all 4 of these hydrogens spread themselves out perfectly evenly if I have 4 unpaired electrons, but they're all, they're in different types of orbitals? And the answer is they hybridize. So we take all 4 of those orbitals and we hybridize them. And the concept of hybridization occurs, and we mix all of those to make 4 degenerate orbitals. And we call these sp3 orbitals. Why? Because we took 1 s and we took 3 p's. So now we have 4 sp3 orbitals. If you're wondering, why don't you put a 2 in front of it, 2 sp3, we just leave that out. It's a convention. Now we have 4 even orbitals, and we have 4 unpaired electrons. Ooh, that electron is a little wonky like that. Okay, so we have 4 unpaired electrons, 4 unpaired electrons in degenerate orbitals. Degenerate orbitals. Okay, now if you're very astute, your next question might be, what does an sp3 orbital look like? Well, the sp3 orbital is 75% p and is 25% s, right? So an s is a sphere, a p is like a peanut or a dumbbell. But this is how we draw it. We draw it with a big lobe like this and a small lobe like that, and then we call it sp3 like that. Now there's an even simpler way to draw it, and that is to just draw the big part of the lobe like this, and then just write sp3. I could bring in one of those Drake memes here, and just say, check mark. That's the way we're going to do it. We just draw a big lobe and we label it sp3. Give me a thumbs up if you follow me on the concept of hybridization. Very important concept for students. Something that you would have seen in General Chemistry 1, but I wanted to review it with you in detail before we really get into the nitty-gritty here. All right. Good. Thanks. Okay, wonderful. Great. If you're confused or whatever, if you have a question, feel free to stop and ask me, and I'll do my best to try to explain it. So a summary of what I just went over on that blank slide was, the ground state electron configuration for carbon, which we know is 1s2, 2s2, 2p2, right? That ground state electron configuration doesn't explain how carbon makes 4 bonds. And so we have to take one of those 2s electrons and we promote it up to a 2p. Then we get 4 unpaired electrons, but they're not equal, are they? Right? Because the 2p is higher in energy than the 2s orbital. And so what we do is we hybridize them. We put them all together into 4 degenerate sp3 orbitals. So now we have 4 unpaired electrons, and they're all in equal energy atomic orbitals. And so that explains why we can have our carbon with 4 unpaired electrons, and we can form a molecule like methane. Again, the sp3 orbital has 25% s character and 75% p character. Look, Instead of drawing your sp3 orbital like this, I'll make it a lot simpler. All you got to do is draw a carbon and then just draw one big lobe. And to let the reader know that it's sp3, you actually write on it, sp3. That way, everybody will unequivocally know you're dealing with an sp3 orbital. All right, so that explains why when you have your methane molecule, okay, if we go back here, when we have our methane molecule, we've got a carbon, right? You've got 4 electrons. So you've got 4, 1, 2, 3. This one's going in the back like this, and this one's coming out in front. So I'll kind of shade it in like this. These are 4 degenerate sp3 orbitals. Okay? And each one of them has an unpaired electron. They're all evenly spaced out. Then if you have 4 hydrogens, right? Hydrogen has 1 unpaired electron. So what does that look like? You have a 1s orbital with an unpaired electron. So you have a hydrogen here. This is a 1s orbital. It's got an unpaired electron. You pair them up, you make a sigma bond. Right? You take another hydrogen. You overlap it like this. This is a hydrogen. It's a 1s orbital. You got 1 electron. You do it here. Here's another hydrogen. This is a 1s orbital. It's got an electron. Here's another hydrogen. This is a 1s orbital. It's got an unpaired electron. And you, my friend, have just made 4 beautiful sigma bonds that explain why methane is tetrahedral, right? Why it's got a tetrahedral molecular geometry like this. So this is called a valence orbital diagram to explain the molecular geometry of methane. Find my slide. There we go. So to make that methane molecule, you take the 1s atomic orbitals of 4 different hydrogen atoms, you overlap them to make 4 sigma bonds, right? So each one of these, this is a sigma bond, this is a sigma bond, this is a sigma, and this is a sigma, okay? You've got to be able to understand and recognize sp3, sp2, and sp hybridization. You've got to understand the relationship between hybridization and bond length and bond strength. Right, that's something that's very important. You probably would have seen that in general chemistry too. And I have a table that summarizes the relationship between hybridization and bond length and bond strength. Before we get into that, though, I want to talk about sp2 hybridization and sp as well, because we're going to look at a lot of carbons that have double bonds and a lot of carbons that have triple bonds. We drew this molecule earlier today, didn't we? Ethylene. Okay, we practiced drawing this. It's C2H4. We drew a beautiful Lewis structure for this, but this carbon has 3 sigma bonds and 1 pi bond, right? Remember from general chemistry that every bond, the first bond between 2 atoms is always a sigma bond, right? This is a sigma bond. Any bond after a sigma is a pi bond. So that means the second bond here, this is a pi bond. A pi bond is the result of the side-to-side overlap of unhybridized orbitals, okay? So in order to form a pi bond, you need to have an unpaired electron in an unhybridized orbital. If we look at that electron configuration of carbon, we promote one of the 2s electrons to a p orbital. We have 4 unpaired electrons, but we only need to form 3 sigma bonds. So we're going to mix 3 of them together to make 3 degenerate sp2 orbitals. And then we're going to leave one of them left over in the 2p orbital, like that. Let me show you what that would look like on my blank page here. So sp2 hybridization. So we have a carbon atom, okay? When it's sp2 hybridized, I'm going to go a little faster now. You've got 3 sp2 hybridized orbitals. Each one has an unpaired electron. And then you're going to have a 2p orbital that has an unhybridized electron. So what's it going to look like? You're going to have 1, 2, 3 sp2 orbitals, all evenly spread out. So what's their geometry going to be? The bond angle is going to be 120 degrees between each of these. And then you're going to have an unhybridized p orbital, which is going to be perpendicular to those. So this is where my artistry skills are pretty bad, but you're going to have a p orbital looking something like this. So this is your 2p orbital. Okay, so when you have the 2 carbon atoms next to each other in the ethylene molecule, you have a 2p orbital like this. Okay, so this is my 2p. This is my 2p. Each one has an unpaired electron, and those are what form the pi bond. Right? You also have the 1, 2. So yeah, these are sp2 orbitals. Right? The overlap head to head to form the sigma bond. So what I've drawn so far is I've drawn this. Okay, here's the pi bond in blue. The sigma bond is in black. Then you have the other sp2 orbitals. So sp2, sp2, like this. Each one of those has an unpaired electron. sp2. Sorry, my artistry isn't the greatest on the iPad. Not that it was that killer on a piece of paper or on the chalkboard, but there we go. So now I've drawn these bonds like this. And then I have a hydrogen, right? This is a 1s orbital, a 1s orbital here. This is a 1s, and this is a 1s, a 1s, 1s. And each one of these is a hydrogen, which I'll label like this. So there's your complete molecule, like a SU. Okay, so that explains sp2 hybridization. All right, so where does the sp2 come from versus the 2p? Well, the hybridization works like this. You have carbon, which is 1s2, 2s2, 2p2. Right, so if you look at the valence electrons, you have 2 in the 2s orbital. You have 3 types of 2p orbitals. You have 1, 2 electrons in here. Again, we're going to promote one of those electrons in here, so we end up with a 2s orbital with 1 unpaired electron. We end up with 2p orbitals. Each one has an unpaired electron. So now we have 4 unpaired electrons, right? But when we have a carbon that has a pi bond, right, attached to it, okay, the sigma bonds, the ones that I'm highlighting in red, those are all hybridized orbitals. The one that's in blue is a pi bond. That comes from the overlap, or the side-to-side overlap of unhybridized 2p orbitals. So when we hybridize these, all we need to do is take 3 of them and mix them together to make an sp2, or 3 degenerate sp2 orbitals. Each one has an unpaired electron. And then you take that one 2p and you leave it by itself, because the 2p is the one that's used to make the pi bond. Okay, and these ones here are all used to make sigma bonds. All right, so let's get back to it here, and we'll take a look. So there we go. So that explains why each one of these carbons in ethylene is trigonal planar. Trigonal planar, like that. Okay, there we go. So if we take a look at the sp2 hybridized carbon, we have the 3 degenerate sp2 orbitals, 1, 2, 3. There they all are. They each have an unpaired electron, right? And then you have, this is the p orbital here. It has 1 unpaired electron, right? What are you seeing in this picture right here? You're seeing this. You're seeing 3 sp2 orbitals. They're all degenerate. They're all in gray. They all have an unpaired electron. Maybe I could put nicer electrons in there. Okay, and then you see the 2p orbital, which has an unpaired electron, right? These are the ones in gray, and then this is the one in red and blue. And that explains, again, why carbon is trigonal planar when it's sp2 hybridized. Now, the shape of the orbital, the sp2 orbital, results from it being 33%, or 1/3 s and 2/3 p. But the way that we, discern between an sp2, an sp3, and an sp orbital in chemistry 30-101 is, look, all you got to do is draw that. Okay, if it's sp3, write sp3. You draw the same thing. If it's sp2, just write sp2, and if it's sp, just write sp. And that's how we discern between the 3 types. So there's the orbital overlap diagram of ethylene. So what you're seeing on this slide is just this molecule. I'd have to draw it small here because I don't have a lot of space. But this is what you're seeing, right? You have the 2 carbon atoms. This is the sigma bond as a result of the overlap between the 2 sp2 orbitals. Here are the other sp2 orbitals over here. They both form sigma bonds with hydrogen atoms. So this is an sp2 and this is an sp2, right? Each carbon has 3 sp2s with unpaired electrons. Each carbon has 1 2p. Okay, this is the 2p orbital. Maybe I'll write it down here. This is the 2p orbital. This is the 2p orbital. And then the pi bond is the result of the side-to-side overlap of the p orbitals, right? A pi bond is actually looks more like this, where you have overlap like that, right? And you might think, well, aren't they overlapping more? Shouldn't a pi bond be stronger than a sigma bond? But the answer is no, it's actually weaker. It's significantly weaker. All right, give me a thumbs up if you follow me on the whole concept of hybridization to make an sp3 or an sp2 hybridized carbon. sp3 hybridized carbons will have a tetrahedral geometry. Their bond angles will be 109.5 degrees. If your carbon is sp2 hybridized, the bond angles will be 120 degrees or close enough, and their molecular geometry will be trigonal planar. Well, we have one other type of hybridization to look at for carbon, and that is an sp hybridized carbon. We'll get to that in a second. So the pi bond, again, is formed by the side-to-side overlap of the 2p orbitals. And so the electron density is spread out above and below the plane of the molecule. There's none from the pi bond in the middle here, but I wouldn't really worry about that a whole lot. And pi bonds are significantly weaker than sigma bonds. What's the significance of that? Really is that when we get into reactions, if you see a molecule that's got a pi bond, you think, it's weaker than a sigma bond. So that's probably where the molecule might react, right? It's because that bond will be broken with greater ease than a straight ahead sigma bond. All right. Let's see here. Let's try this question. This is question 1.22 from our textbook. This will be a fair game question for the next quiz. It just says, if you have a formaldehyde molecule, identify the types of bonds that form the carbon-oxygen double bond, identify the atomic orbitals that form each carbon-hydrogen bond, and what type of orbitals do the lone pairs occupy. So we'll start by drawing the formaldehyde molecule, which is this. So it's that's the molecular formula for formaldehyde. So we have the hydrogen bound to carbon, and we have the double bond to oxygen, and the oxygen has 2 bonds and 2 lone pairs. So there's my formaldehyde molecule. Now, if I just zoom in on it, the first question was, what are the types of bonds? Well, if I highlight these bonds, let's see, will this work? If I highlight this in red, this one in red, and this one in red, could anybody tell me what types of bonds I've highlighted in red? And it's not a trick question. What types of bonds are the ones highlighted in red? Yeah, exactly. Those are the sigma bonds, right? So sigma, this one is a sigma, this one is a sigma. There's one other type of bond here, isn't there? There's this one here, the blue one, which is a what?
Pi bond.
Absolutely. We have a pi bond here. Now, if you're the kind of person who likes to split hairs, and if you're saying, well, Mr. Dion, couldn't you have highlighted this one in blue and called that the pi bond? The one on the left? It doesn't matter. It's neither here nor there. It doesn't matter at all. Okay, just one of them is sigma, one of them is pi. So now we've finished the first part. We've identified all the different types of bonds. We have 3 sigma bonds, and we have 1 pi bond. So we identified the bonds in the double bond. One is sigma, right? We have 1 sigma and 1 pi in the double bond. Well, if we identify the types of orbitals that are in each carbon-hydrogen bond, let's draw a little bit bigger here. Could anybody tell me what the hybridization of the carbon is, and it's not a trick? I'll redraw the molecule while you're thinking about it. What's the hybridization of that carbon? Is it sp3 or sp2? It's got 3 sigma bonds and 1 pi bond. Right, so it's sp2, right? The only time carbon's going to be sp3 is when it has 4 sigma bonds. So this carbon is sp2 hybridized. That means the bond angles are all going to be around 120 degrees, right? The molecule is trigonal, or the molecular geometry is trigonal planar. Okay. Now, it says identify the atomic orbitals that form each carbon-hydrogen bond. Well, if my carbon is sp2 hybridized, right, that means it's going to have 3 sp2 orbitals. So it's going to have an sp2 orbital like this. It's going to have another sp2 orbital like this. It's going to have a third sp2 orbital like this. Each one is going to have an unpaired electron in it. So when the hydrogen overlaps, hydrogen doesn't hybridize. You have the 1s orbital, and it's going to have an unpaired electron. Right? That's our hydrogen. Here's another hydrogen. It's a 1s orbital with 1 unpaired electrons. And so the answer to B is you have an sp2 from the carbon, which is overlapping with a 1s from the hydrogen, right? This is from the carbon, and this is from the hydrogen, like that. Now it's asking me what type of orbitals do the lone pairs occupy? Could anybody tell me what the hybridization of the oxygen is? If I look at the oxygen is 1s2, oops, 1s2, 2s2, 2p what? 2p4. So I've got a 2s orbital, and I've got 3 2p orbitals. I've got 2 electrons in here, and I have 1, 2, 3, 4 in here. Well, in order for me to have the oxygen having the lone pairs in the sigma bond in degenerate orbitals, I'm going to have to hybridize these to make 3 sp2 orbitals and have my 2p orbital with an unpaired electron in it, right? I'm going to have 1, 2, 3, 4, 5 electrons in my hybridized sp2 orbitals, and each one of these represents a lone pair, right? This is a lone pair, and this is a lone pair. So if I draw my oxygen, and I'm going to have to move this a little bit to draw a proper orbital overlap diagram, I'm going to draw the oxygen atom and its orbitals in blue. I'll have my oxygen up here. It's got 1 sp2 orbital with an unpaired electron. That's this one. It's got 2 more hybridized sp2 orbitals with 1 lone pair, the other lone pair. So this is sp2. It's got the lone pair. So the answer is sp2 for the lone pairs. The only thing that I haven't drawn here is the pi bond, right? Because everything that I've drawn here, this is a sigma bond, this is a sigma bond, and this represents a sigma bond. Well, where does the pi bond come from? I've got a 2p orbital on my oxygen, right? The 2p orbital here. So that's this one. It's got an unpaired electron in it. And I've got a 2p on my carbon too. Right? This is a 2p orbital. It's unhybridized. It's got an unpaired electron. And that is what results in the pi bond. So this is the pi bond, like that. So the answer is the bonds that make up the carbon-oxygen double bond are a sigma and a pi. The types of orbitals that form each carbon-hydrogen bond are an sp2 from the carbon, that's a hybridized orbital, and a 1s from the hydrogen, which cannot hybridize. And what type of atomic orbitals are the lone pairs on the oxygen in? Right, these lone pairs, there's 2 of them here, they're both in sp2 orbitals, hybrid orbitals, but they're paired up. And there you go, there's the orbital overlap diagram for formaldehyde. Well, let's take it one step further. Let's talk about the last type of hybridization, which is sp. I'll go a little quicker here because we've already covered sp3 and sp2 in depth. If you understand those, you'll understand the hybridization to form an sp hybrid orbital. So if we have acetylene, right, what types of bonds do we have for the carbons in acetylene? Right, the first bond is a sigma bond. These are sigma bonds. Right, but you have 2 pi bonds. 1, 2 pi bonds. Right, there's 2 of them. So we need 2 unhybridized 2p orbitals. Right, we need a 2p and a 2p. each one with an unpaired electron. So how would we do that? We have our excited electron into the 2p. We only need to hybridize 2 orbitals to make an sp, or 2 sp orbitals that are degenerate. And then we have the 2p's left over, right? The 2p's are the ones that are going to make the 2 pi bonds. And then you have these sp orbitals, which are the ones that are going to form the sigma bonds. Like that. And there you go. So there's the orbital overlap diagram of acetylene, right? What are you seeing on this slide? You're seeing this. You're seeing the carbon with a triple bond to the other carbon, and you've got a hydrogen here and a hydrogen here. All right, if we label the orbitals, each one of the carbons has an sp. This is an sp, so this one is an sp, and this one has an sp. They each have 1 unpaired electron, right? Each hydrogen is a 1s. They each have an unpaired electron, so that means that this is a sigma bond. This is a sigma bond, right? That's this one and this one. We also have a sigma bond here in between the 2 carbons. That's this one here. And then we have 2 pi bonds. And it's tough to draw them, but you have 1 p orbital here on 1 carbon, here on the other one. They overlap to form 1 pi bond, and then you have the other one. I'll highlight it in green. One's going in the back like this. That's the other 2p, and those overlap as well to form the other pi bond. So again, this is a 2p, this is a 2p, this is a 2p, and this is a 2p, like that. So there's the orbital overlap diagram for acetylene. All right, so nemetin is a compound that was first isolated in the 1940s, has potent antibacterial activity. Its structure was verified recently. It was made in the laboratory. I don't know what this has to do with anything, but determine the hybridization state of each carbon in nemetin. Now, to summarize, what did we learn? We learned that when carbon has 4 sigma bonds, it's sp3 hybridized. When carbon has a double bond and 2 single bonds, it's sp2 hybridized. And when carbon has a triple bond and a single bond, it's sp hybridized. So if I was to highlight this carbon in green, could anybody tell me what the hybridization of that carbon is? And it's not a trick. Absolutely. Thanks, Kayla. That would be sp hybridized, right? Why? Because it's got a single and a triple bond. So other sp hybridized carbons would be this one, this one, this one. Another carbon that would be sp hybridized, I guess, would be the one that's got the 2 pi bonds and the 2 single bonds as well. So that would mean this one here would be sp hybridized, and that covers that. What about this one? If I highlight this one in yellow, could anybody tell me what the hybridization of that carbon would be? It's sp2. Yeah. So this one would be, oops, this would be, there we go, sp2. Why? Because it's got 2 sigma bonds and 3 sigma bonds and a pi bond. So it's got a double and 2 singles. So it's sp2. Other sp2 hybridized carbons would be this one and this one. And then if I look at the other carbons, so if I highlight this one, and this one, these are all sp3, right? Because they all have 4 single bonds. So you've got to be able to look at a molecule and recognize, you know, which carbons are sp2, which carbons are sp, which carbons are sp3 hybridized. Now, I promised you that I would talk about the relationship between hybridization, bond length, and bond strength. A number of years ago, one of the first questions on an ACS final dealt with this. So you have to understand the rationale behind this table here. So here we have ethane, ethylene, and acetylene. So we're comparing a single bond to a double bond to a triple bond. What happens to the bond length as we go from from a single to a double to a triple is you see that the bond length decreases, right? It gets shorter and shorter. Why is that? It's really just because the more orbitals that you have that have to overlap to form bonds, the closer the carbon atoms have to get together. Now, bond energy, I think, is even more intuitive. You know, you think about it, the more orbital overlap that you have, the stronger the bonds get, right? And so as you go from that single to a double to a triple, the bonds get stronger and stronger and stronger just because you have more orbitals overlapping, and therefore they get stronger. So again, you've got to know the trends here. That would make a really easy question for the first quiz, for me to ask you the relationship between bond length and bond strength when we're dealing with hybridization, whether we've got an sp3 hybridized carbon, you know, an sp2 hybridized carbon, and an sp hybridized carbon like that. So there we go, hybridization, quite a bit of time on that. It says indicate these bonds or rank them in terms of their bond length. So if I call this first one, I call this bond number 1, I'll call this 2, and I'll call this number 3. It's kind of funny because it goes from a single to a double to a triple. Well, if we go from shortest to longest, right? Number 3 is going to be the shortest. Number 1 is going to be the longest. Number 2 will be somewhere in the middle, right? Because we know that when we have two sp3 hybridized carbons, they only have a single bond between them. When we have two sp2 hybridized carbons, we have not only the overlap of the sp2 hybrid orbitals, but also the overlap of the 2p orbitals. And then when we have two sp hybridized carbons, we have the overlap of the sp hybrid orbitals, but also the overlap of two 2p orbitals to make two pi bonds. There you go. So the relationship between bond length and bond strength.